For the introduction, Sammy. As you mentioned, I'm a professor in engineering, specifically with the reliability engineering program in the Department of Mechanical Engineering. And I'm going to be talking today about human performance modeling and experimentation, specifically how to quantify human performance and how to capture it for integration into design decisions, specifically for different immersive environments. So the type of environments that we're particularly interested in are safety critical systems. So these are systems where when the user interacts with them, if there's a potential error, there could be a devastating consequence like death or serious injury. So these are systems that commonly appear in domains such as healthcare and energy and defense, just to name a few. And what the challenge is with these systems when you're designing them is actually being able to test them on the user while not compromising their safety or the safety of the overall system, which is particularly challenging given the requirements for design validation, which is required by most regulatory agencies, meaning that you actually have to take the safety critical system that's being designed and prove that it actually operates in the way that you intend it to, particularly with the intended user population. So the way this works is that you actually take a segment or some sample of the target population, and then you immerse them into what would be considered a replica or an environment that's intended to replicate this safety critical system in what's known as simulated use testing. So this is commonly used in the product development process at various stages to try to test out different features and functions and also test out different design specifications. Now, how we do this in my lab is specifically, we have several different immersive forms of media, but the one used most commonly is our virtual reality cave, which is a 3-side back projected immersive room, basically a 10 by 10 room that's open in the front. And what this allows us to do as an alternative to HMDs is actually to bring physical objects into the virtual environment. So we can bring in a desk, a keyboard, all of these things that you might use for natural system interactions. So we can have a bit more flexibility with the types of components we test. And the systems we're particularly interested in are semi-autonomous systems. So pretty much every safety critical domain has some type of semi-autonomous system where the human is not required to manually operate the system, but it's being operated potentially remotely. And then the human has to monitor the system. And then when there's need for intervention, they have to know that the need is required and then intervene at the appropriate time. And so this is the basic parameters of a semi-autonomous system. The issue, of course, is that these systems tend to be high cognitive burden, lots of errors, and the errors are quite pervasive. And of course, as I mentioned, they can have pretty devastating consequences. So these are really important systems to study, and we looked at them in several different types of applications that I'll talk about in a moment. And the main ways that we evaluate these systems, 3 main outcomes that we look at. One is neurophysiology, which are indirect measures of cognitive workload. So we have a variety of biosensors that I'll talk about. Also ergonomic response. These are mostly static-based interactions or static seated based interactions. So the ergonomics of the workstation design is really important, and also perceived response. So what's the subjective workload that the user is experiencing? So we look at this from kind of a multifaceted perspective in terms of different performance measures. So one of the examples that I'll talk about, I mentioned some of the safety critical domains. So in healthcare, a few years ago, we worked with MedStar Washington Hospital Center, which is not too far from campus. They have the largest hospital telemetry unit in the area, over 200 beds, which for those of you who don't know, telemetry units are basically remote monitoring stations. So this is healthcare's version of a semi-autonomous kind of control room. Every domain has something like this. This is healthcare's version. So I'm just going to play you a quick video and then we'll talk about it. Okay, I'm going to stop it there. So this is basically a video we took when we visited the telemetry center. What you'll notice is that there's these operators sitting in front of multiple screens. There's actually, you can't see this, but there's 16 patients per screen, 4 screens total, 64 patients total. So these operators are sitting there for these really long shifts. And there's an alert that potentially comes in that'll tell you that a patient vital is outside of what would be considered an acceptable threshold. And then they have to evaluate that information and then perform a subsequent set of steps. Now, of course, where the issues arise is when there's missed signals, which it's notable that there have been widely reported issues with missed signals and also issues with accuracy and response to signals. Unfortunately, these don't necessarily get publicly released, but this is something that a lot of hospitals have to deal with in terms of errors. So some of the questions we have in regards to this is, what's the best way to design these workstations for longevity, for these long shifts? What's the maximum number of patients that an operator can review or can monitor at one time without exceeding what would be considered their cognitive burden threshold? And so these were all questions that we had. Also, what's the best way to visualize this information? So this is an example of something we could look at in the virtual reality cave, which we did develop several different simulations of that, modifying the type of information that was displayed in terms of the information visualization, and also modifying the number of patients that controlling this in an experimental simulation, a number of patients that you had to simultaneously interact with when trying to get more information about a particular scenario. So this is, again, one example. This is a healthcare control room. So the main question that we're interested in answering is, what impact do design specifications have on human performance? So we're looking at a few different things there. One of the items we look at is sensory cues. So we want to know what's the best way to communicate that there's critical information that needs to be attended to. So auditory sensory cues in the virtual reality cave I mentioned previously, we have 7-point surround sound. So we can simulate the directionality of information that's coming in, and also different characteristics of the auditory signal, which is really important to simulate, as you saw, kind of that 360 view of the telemetry room, having signals coming from workstations that don't particularly pertain to the operator tasks right in front of them. Also visual cues. So there's many different visual characteristics of the cues that can be controlled in the experiment. And then tactile cues, which are also commonly used in certain domains. You can see here at the bottom of the screen, a vibrotactile bracelet at the bottom left, one that we designed and prototyped in the lab for one of our experiments. And then right next to that, a commercial cyber glove, specifically the Cyber Touch, also used for vibrotactile simulation and hand tracking. So that's for the sensory cues. We also look at different interaction modalities. So using the same cyber glove that I just mentioned, we can do touchscreen, virtual touchscreen interaction. We can also interact with hardware, physical hardware that you would typically see in a control room environment, like a mouse and a keyboard. We can integrate those in the virtual space. We could do gesture recognition and also wand navigation. So these are some of the variables from the interaction modality perspective that we would modify within experiments in the virtual reality cave. And then finally, from the workstation design perspective, different data visualization approaches. I mentioned that previously. We've also looked at previously screen orientation and layout. So what's the best way to orient the screens in terms of stacked or parallel or curved designs that would facilitate fast response? to the information and not elicit too much peripheral information that needs to be gathered. We've also looked at information architecture. So how does one navigate the information that's provided to them on the virtual screens? So again, these are just examples of the design specifications that we're particularly interested in looking at for these semi-autonomous systems. And the measures that are collected, there's two main types. For the objective performance metrics, one of the main tools that we use are eye tracking glasses. So you'll see in the upper right hand corner right here, these are pupillometry eye tracking glasses. This is a SMI VR glasses, and you'll see optical sensors right here. And this is, those optical sensors communicate with our ATR system, our ATR optical tracking system. With the VR cave allows us to track the head positioning. And also what you'll see is two cameras. Well, it's a little hard to see from this image, but there's a camera pointed inwards at the eye, which tracks the pupil diameter, which is the indirect measure of stress and cognitive workload. And then there's a camera pointed outwards at the visual scene that tracks what the user is looking at a particular time, which is important not just from the perspective of capturing a visual representation of that, but also because it gives us a time flag, so a marker that when someone is looking at a specific thing at a specific time. So if there's an alert that goes off on a particular screen on the interface, we can track the point at which the user's attention is fixated on that, and then determine the time from that point to when they perform some subsequent action. So that's all critical information to understand response time. We also look at accuracy, which is domain specific based on the outcome of the task. And then I mentioned neurophysiological sensing, so the pupillometry, but we also look at a variety of other biosensing measures. In the bottom right-hand corner, you'll see one of the custom biosensors that we built in the lab. This one is a chest strap that looks at breathing rate, heart rate, and also heart rate variability and temperature. We also have a galvanic skin response biosensor that looks at the sweat conductivity of the skin. These are all, again, indirect measures of cognitive workload and stress. And we also use a variety of commercial biosensing tools as well, depending on the experiment. So these are our objective performance metrics. To make a more robust experimental design, we also combine those with subjective performance metrics. So actually asking the individual what their level of workload or difficulty is for specific tasks. And a main piece of this and what is kind of the foundation for our work is this idea of cognitive decomposition. So actually taking every discrete task that the user performs and cognitively decomposing that, which then gives us more information to try to tweak design specifications and really target design risk mitigation strategies. So at the lowest level of cognitive complexity, and this is decomposed based on taxonomies, cognitive and psychomotor taxonomies. So at the lowest level of cognitive taxonomies, you have sensory-based and memory-based activities that have to be performed. So these are things that, that do not require conscious control. So lower cognitive complexity, automatic processing. And then as you move up the scale to higher levels of complexity, you get tasks like decision-making and problem solving, where you have to take in new information. So the information that you get, your salient sensory cues and the things that you're recalling from memory, you then take that information, process it and act on it in a subsequent decision. And so we decompose all of these into tasks, which then allow us to tie all of the measures that I talked about to specific discrete cognitive steps that the user is performing in this virtual environment. And again, allowing us to then target specific strategies, design strategies based on how we're organizing the experiment and what variables we're controlling. So here's one of the recent Studies we did, we did 2 related studies on control rooms, one funded by the U.S. Nuclear Regulatory Commission, another by NAVAIR. And the one that was specifically funded by Navy, you can see here to the right, this is actually unmanned aerial vehicle control panel. It's a quad, a kind of generic quad control panel that we developed with the Human Performance Systems division of NAVAIR. And we replicated this in the VR cave. What the Navy was specifically interested in is they were going to invest money into different sensory systems. So they wanted to know, for example, for visual, auditory, like an auditory beep, a tactile, and then an auditory voice-based cueing system, is more better. So should they invest money into all of these different cueing systems, or if at some point is more or less, meaning the more cueing that you throw at the operator, does it at some point start to degrade performance? And that's in fact what we found. We just recently published a paper on the results of this, which showed that in fact, more is not better, and that exceeding, we saw a variety of different outcomes, but we found a threshold that if exceeded would actually degrade specific types of cognitive activities. So this is an example of a study. Another one, a very recent one, which actually the official start date of this is on Monday, also funded through the Navy. So this is a project that just got awarded, kind of an extension or a jump off of the one that I just talked about. And this is looking at mixed reality. So a lot of these systems for control rooms, as I mentioned, in these semi-autonomous control systems, they involve mixing physical hardware with virtual systems. So you're using these physical devices to interact with some type of virtual modality. And what we don't have information on, particularly empirically valid human performance information, is what physical modalities are best and what virtual modalities are best. And in combination, what's the impact of going from physical to virtual and back to physical? We have no empirical evidence to support that. And so a lot of the design decisions are being made based on legacy systems. They're being made based on physical and other resource constraints, which is not great from the human performance perspective. So we actually sought to define human performance information for how you would mix these physical and virtual modalities in basically an optimal combinatorial fashion based on maximizing human performance. And so again, this is an upcoming project that we're gonna start next week, kind of building on some of the prior work in the virtual reality cave. So again, those are examples of some of the things we do. Some additional related research to some of the defense and healthcare examples are system component personalization. So we do a lot of work related to identification of subpopulation characteristics and population clustering, with the idea that if you can identify that, you can tailor specific component specifications to those statistically relevant subpopulations. Also, human performance optimization of hybrid system design. So this is not just based on specific performance outcomes, but also more practical issues such as costs and manufacturing and things that sometimes don't get integrated together with human performance estimation. So being able to take the output from what we learned from the immersive experiments and integrate it with other development information. And then finally, working with regulatory agencies to develop empirically valid standards for simulated use testing in these immersive environments, which we work a lot with the Food and Drug Administration and NRC on that. And some thoughts on future research, some things that we're currently working on are adaptive systems. So I mentioned the biosensors. So being able to sense the extent to which someone is about to exceed what would be considered an acceptable threshold for cognitive workload. and to modify in real time what they're experiencing or what they're interacting with through the display interface. So basically like a form of behavioral closed loop control. And also mobile AR information displays. So a lot of what I talked about was this idea of developing best practices for these semi-autonomous system controls. So once you do that, the next step would then be for space-constrained situations where you don't necessarily have the space to really implement this in the way that might be optimal, to basically store it in your pocket and take it out as necessary. And that's something that a lot of the various human performance divisions of the federal agencies have expressed interest in pairing with this research. So I will end there.